Hello, welcome to JART's online training for UA Local 516 members. Today we are going to review the low pressure control and how to set up this control in 3 different types of installations. If you got a PT chart handy, you might want to use it to follow along. A low pressure control is typically used in one of 2 ways, either as a safety or an operator. A system utilizing a low pressure control as an operator would typically be a pump down system, or a unit that uses the low pressure control as a thermostat. This is when our low pressure control gets renamed, and we now refer to it as a pressure stat. Let's take the low pressure control as a safety first, and we'll review how these are set up. Here we have a typical 134A walk-in cooler. Condensing unit sits on top of the box and the evaporator sits right inside the cooler. We'll add some wiring to this, and we'll use a thermostat to cycle the unit on and off. And since we're using a thermostat, it must have control over the compressor at all times. The low pressure control is there as a safety only. If we take a look at the ladder diagram for this unit, we can see that the low pressure control is shown normally closed in the de-energized state. And this is a standard wiring convention for ladder diagrams, and this clearly indicate that the low pressure control is a safety for the compressor. By contrast, our thermostat is shown normally open in the de-energized state. And again, this is a standard wiring convention for ladder diagrams to show that this thermostat is the control for this compressor. We'll apply some power to this unit. And as you can see, absolutely nothing is going to happen until the thermostat calls for cooling. The low pressure control should remain closed for the entire on and off cycle of this refrigeration system. So how do we set up a low pressure control as a safety? Well, we're still working on our 134A cooler, and the normal range of suction pressure that this compressor should see should be between 33 and 20 psi, somewhere in that range. We need to ensure that the low pressure control will not interfere with the normal operation, but still be able to terminate the circuit if it senses a lower pressure. By cutting in below our normal operating pressure and cutting out about 15 psi below that, we can be assured that our low pressure control will not interfere with the thermostat's control of the system, but still give us a safety margin if we do run out of gas, or if there's a problem with the expansion valve or a plug dryer or any number of things that could limit the flow of liquid refrigerant to the low side of the system. So now that we have our numbers, we're going to take them directly over to our low pressure control. You'll often see at the bottom of the low pressure control, cut out is cut in minus differential. We have our cut in on the right in this instance and the differential on the left. Now please take note, not all pressure controls are the same. You must take a close look to see which is the pressure control you're dealing with. So we're going to set up our pressures. We always set the cut in first. We'll get out our screwdriver and adjust close to what we think our cut in will be. Now you'll notice I have this control set at 21 and I want it to be at 17. It's important to remember that the numbers on the pressure control are a guide at best. They're less reliable than a plumber's estimate. So please remember, when you're adjusting these, you must get out your gauges and confirm that your cut in and cut out settings are exactly what you want them to be. There is no shortcut. I'm not trying to be condescending in this portion of the video, but one of the things that I have learned in my few short years of teaching here at JARTS is how many people have not had the opportunity to work on a system that has valves. I just want to do a very short tutorial on how to attach your gauges to a service valve. You're going to need to know how to do this in order to adjust your low pressure control. Now you can do this while the compressor is running. It's completely safe. First step is to remove the valve cap stem, and yes, this is the biggest wrench I could find. Next, you need to ensure that the valve is fully back seated. Now you don't need to torque it down, a firm push is all you need to snug it up. Then remove the cap and install your gauge hose. Finally, crack open the valve stem by winding it in. Half a turn is usually more than sufficient. Next, put the valve cap back on. Next, we'll take a look at how a low pressure control works in a pump down system. A pump down system is a unit that will typically use a liquid line solenoid to stop the flow of refrigerant from the receiver to the evaporator on the off cycle. In this example, we have a 404A condensing unit on the roof, a walk-in cooler down below in the building. A liquid line solenoid, right down here, is in the box next to the expansion valve, and it is directly controlled by the thermostat. When we apply power to the unit, you'll notice that unless the thermostat is calling, nothing is going to happen. Now, when a thermostat does call for cooling, it will energize the liquid line solenoid valve. And when that happens, you'll notice your low side gauge will begin to rise in pressure. That's our liquid refrigerant flowing through the evaporator. Once it reaches the pressure that we've set on our low pressure control, the unit will become energized. And we'll have the magic of refrigeration until the thermostat is satisfied. If we take a look at our ladder diagram for this pump down system, turn the disconnect on, the evaporator fan motors come on, and again nothing else happens until the thermostat makes. When the thermostat makes, the liquid line solenoid will energize, and when that low pressure hits the low pressure control's cut-in point, the compressor will turn on. The compressor will continue to run until the low pressure control tells it to stop. And the only thing that should make that happen is the thermostat dropping out of the circuit. If the box is satisfied on temperature, the thermostat drops out, the liquid line solenoid is now closed, and you'll notice your low side pressure begin to drop. It'll continue to drop until the suction pressure hits our cut-out point, in which case the low pressure control will turn off. You may notice I have the thermostat and the liquid line solenoid coming after the evaporator fan disconnect. This is a really good idea. When someone comes into the walk-in cooler to turn off the fans because it's too cold and they want to load Coke into it, it's no problem. They've turned off the fans, they've also turned off power to the liquid line solenoid. And in a matter of minutes, the low pressure control will turn the compressor off. Now you don't have a frozen up coil. Now, just to show you graphically what's going to happen to our system during a pump down sequence, our thermostat will take our liquid line solenoid out of the circuit, and you'll begin to notice the compressor will pump down. Your low side pressure will begin to drop, and it'll continue to drop until we hit our cut out pressure. Once we hit that pressure, the system will stop, and it'll stay off unless the low pressure control energizes the compressor again. So, how do we set up a low pressure control for a pump down system? Well, some people say it doesn't really matter. But Sportland tells us that a good rule of thumb is to cut in at 50% of your normal operating pressure. This is so that you can be assured that the low pressure control will definitely turn on the compressor and not interfere with the thermostat's control of the box temperature. The normal operating range for our 404A walk-in cooler is anywhere between 87 and 60 psi. So we're going to set our cutout at somewhere in the 44 psi range. Again, you need to attach your low side gauge to confirm the cut in and cut out settings. The numbers on the control are a guide at best. Once you have the cut in set, you can then move to the differential or cut out, however the manufacturer's labeled it. And in this case, we're going to set it for approximately 15 psi. It's important that you don't let the system pump down into a vacuum. It's not necessary, and if there is a leak, you've just brought non-condensables into the system. The last system we're going to hook up is our pressure control used for the box temperature, or the pressure stat. In this case, we've got a walk-in cooler again. It's going to be a 404A system. We'll throw some power to it, and as you can see, it is a very simple system. We have a dual pressure control, and that is all. The temperature we want in our walk-in cooler is going to be about 35 degrees Fahrenheit, our average box temperature. And our standard evaporator coil is going to give us a 10 to 15 degree TD. A lot of this is going to depend on your pipe size as well, or if you have a very long run. The maximum temperature we can have in a walk-in cooler is 40 degrees Fahrenheit. Now, if you do happen to have a 40 degree Fahrenheit box, chances are the health inspector is not going to be very happy with you. They like to see it below that. For freezers, it's always 0 degrees Fahrenheit or lower. 0 degrees is the maximum temperature you're allowed in a freezer for food. So the maximum temperature we're going to have in our walk-in cooler is going to be 38 degrees. That's going to equate to a cut-in pressure for our pressure stat of 83.5 psi. Remember, every PT chart is a little bit different, so these numbers might not be exact with the numbers that you're using, but they're going to be close enough. Next, we need to set our pressure control. All we have to do is adjust our cut in till we get to approximately 83. And again, we'll check this with our gauge to make sure that is in fact the number we're cutting in at. The next step is to find out what TD we actually have on our system. I've got a brand new installation here with a 75 degree box temperature and my pressure control set for 60 and 10. Well, we know we want our pressure control to be set at about 83. And we'll turn the power on and let it run. Throw some gauges on and change that to temperature. And we can correlate between the box temperature and the temperature I'm getting on my gauge set to tell me what kind of a TD this system has. As you can see with the numbers that are running now, I've got approximately a 15 degree TD on this coil. And this is an important number to help us set our differential or our cut out. So we know our maximum box temperature that we want is going to be about 38 degrees Fahrenheit. That's going to equate to approximately 83 psi. We also know the minimum temperature we want in our box is going to be 34 degrees Fahrenheit. We've discovered that our coil has a 15 degree TD, so when the coil temperature reaches 19 degrees Fahrenheit, we want the system to shut off. This is going to equate to 55 psi. We can't set our differential to 55. 55 is where our cutout is. So we'll take our 83.5 minus our 55, and that's going to give us a differential setting of approximately 28 psi. And that's where we'll set our differential to on our pressure control. We'll turn the power on and let this run. Now I'll speed the time up considerably so we don't have to wait around. As you can see, our system is shut off at 35 degrees and will cut in again at about 38 or 39. It's important to remember when you are setting up your low pressure control as a pressure stat, you need to figure out your TD by taking your suction pressure at the compressor. If you've got a very long piping run, or if your pipe size is marginal, this becomes absolutely crucial. Because of long line runs or undersized piping, the pressure you read here can be significantly different than the pressure you read in your compressor. Thank you for watching JART's online training for UA 516 members.